Good day everyone. In today's lecture, we'll be discussing about the measurement of mutual inductance using Heaviside bridge, and we'll also be discussing about Campbell's modification of Heaviside bridge, and in the second part of the lecture, we'll be discussing about the measurement of frequency using a Wein bridge. We will start discussion about a Heaviside mutual inductance bridge. Now this Heaviside bridge, it is used to measure the values of mutual inductance in terms of a non-self inductance. Okay. Now let us see what are all the components that are present in a Heaviside mutual inductance bridge. Now looking at this, we know that we have a component M. This is called as the unknown mutual inductance. Then L1 is the self inductance of the secondary of mutual inductance, and L2 is a known self inductance quantity that we are connecting in the second arm. Then we have four resistors R1, R2, R3 and R4. All these resistors are non-inductive in nature, that is they are purely resistive. They do not have any inductive components in them. Okay, now let us move further. So this is the bridge. Here we have four arms, the first arm, the second arm, the four arms we are having. A source of supply E is connected. Now from the source of supply, current I1 plus I2 is proceeding out, and I2 is passing in the second arm, I1 is passing to the first arm and going to the third arm, I2 is passing to the second arm and going to the fourth arm. Now moving further, let us look into the derivation of this Heaviside mutual inductance bridge. Now from the diagram we can make out that the voltage drop between the points BC, that is the voltage drop between the point BC and the voltage drop between the point DC is equal. When it is equal? It is equal at bridge balance condition. Bridge balance is the condition where no current is flowing through the detector. Now at this condition, I can clearly write I1 R3 is equal to I2 R4, and I can modify this in as I1 is equal to I2 into R4 divided by R3. And the second thing that I can write is the voltage drop across the point ABC, that is the upper arm, is equal to the voltage drop across the point ADC, the lower arm. Now this is also possible at bridge balance condition. Now moving further, I can write here that the mutual inductance component, through the mutual inductance component, which current is entering? The current I1 plus I2 is entering in the mutual inductance component. So I'll write it to be I1 plus I2 j omega m, because this will be present in the first term. This will be the mutual inductance is because of L1, and this is the unknown quantity. Then I can write in the first arm current I1 is entering, therefore I1 plus R1 plus R3, that is the upper arm full I am considering, plus j omega L1. This is the other components. This will be equal to the current I2 that is entering through the lower arm. Current I2 is entering, it is passing across R2, R4 and L4. Therefore I will write this to be I2 into R2 plus R4 plus j omega L2. Now what I will do is from the previous equation, I know what is the value of I1. Now here I can see the equation is in terms of I1 and I2, therefore solving this is not possible. Therefore I have to change this I1 quantity in terms of I2. So previously itself I have derived what is the value of I1. So I will substitute its value. Substituting its value and solving for real part and imaginary part, I get the expression, that is R1 is equal to R2 into R3 by R4. So R1 is the component that is non-inductive resistance in the first branch. Now this is the component that I have to derive, that is the mutual inductance component M. So I can write M is equal to, from this expression separating the imaginary part, I will get M is equal to L2 minus L1 into R4 by R3. I'll get this thing. Simplifying it further, so this is the expression of M that I am getting. So I can write it to be R3L2 minus R4L1 divided by R3 plus R4. Now if I am considering this R3 resistance and R4 resistance are equal, that is this is the known value of resistances that I am connecting. Now I'll select it to be equal. For example 10 ohm and 10 ohm, if I am selecting this, then I can get R3 and R4 when it becomes equal. This R3 plus R4, this will become 2. Okay, and I can remove this out to be common. I will get L2 minus L1 divided by 2 when R1 is equal to, and also substituting here I'll get R1 is equal to R2. So these are the two expressions that I am getting. Now we will be moving on to the next modification, that is Campbell's modification. Before moving on to Campbell's modification, we have to derive a small formula we have to derive. Now what I am doing is, I know what is the value of M from solving the imaginary part. Now from this I will try to derive what is the value of L2. Now I am trying to derive the value of L2. L2 is equal to M into R3 plus R4, R4 plus L1. In this manner I am getting what is the value of L2. Now what I will do, again as I have considered, when R3 is equal to R4, I am considering the same situation. Considering the same situation, I will get the value of L2 is equal to 2M plus L1 and R1 is equal to R2 I am getting. Now this expression that we have seen here, this expression I will be using for the Campbell's modification. So we have to keep this expression in mind. Now let us move further. Let us look into the Phasor diagram. Now looking into the Phasor diagram, what we can clearly see here is that I am taking a reference, that is I1. I am taking it to be reference, and we can clearly see that the current, that is the voltage drop across the first arm, is I1 into R1. So I can also write, as I1 is in this phase, the voltage drop across resistors will always be in the same phase. Then I can also write I1 R3. These two components I am getting because for a resistor, current and voltage will always be in phase. So these three components I have mentioned. Then we know that the voltage will always lead for an inductor. So in that manner I am getting I1 omega L1. Now when I am talking about this inductor, the first inductor, it is having a mutual inductance, that is a mutual inductance component is also there. This mutual inductance component is I1 plus I2 omega M. So this is also getting added, and the level, and I get this level. I will be getting this level. Now to derive what is the value of E1, what I will do is, I will just take a phasor sum in between I1 R1 and I1 omega L1 plus I1 plus I2 omega M, because this is the first arm. I will just take a phasor sum of this. Taking a phasor sum, I get the value of E1. This is the value of E1 that I am getting. So talking in bridge balance condition, E1 and E2 will be similar. So this is E2. Now E2, as looking at the second branch also I can make out, it also has two components, that is I2 omega L2 and I2 R2. So if I am resolving this, these are the two components that I am getting. So that is why I have written I1 R1 is equal to I2 R2 and I1 omega L1 plus I1 plus I2 omega M, which is equal to I2 omega L2. So in this manner I am getting E1 and E2 I am getting. Okay, so this is E1 and E2, this point. Then talking about the third arm. So in the third arm I have already told I1 R3. So we know that under bridge balance condition, E3 and E4 will be equal. Therefore I can write this I1 R3 and I2 R4. Therefore the current component, both will be in phase. I1 and I2 will be in phase. So this is my E3, this is my E1. To find out E, what I have to do? I have to take the phasor sum of E1 plus E3. So I am just taking the phasor sum. Taking the phasor sum, I am getting the E quantity. So from here we can clearly make out the full voltage E. It is leading the current I1 and I2 that is flowing through the upper branch and the lower branch. So this is the phasor diagram for Heaviside's mutual inductance bridge. Now moving further, let us move into the Campbell's modification of Heaviside's bridge. Now this is used to measure the self inductance in terms of mutual inductance. That is, I have to find out what is the value of L2. This L2 I am having. I have to find out what is the value of L2. This will be measured in terms of the known values of mutual inductance. Right. So previously, as we have discussed, so these two bridges are almost similar. So looking at this, we can clearly make out here in the first arm I am having L1 R1. In the second arm I am having L2 R2. So in this similar manner, this bridge is very similar. Only an additional component R is added in the first arm, and an additional component L and R is added in the second arm. Right. So let us look into how we will get. Now for this, we can see here that a switch connection is there. Now using this switch connection, we will take two sets of reading. We will take two sets of reading, one with switch open and other with switch closed. Now when I am opening this switch, I'll calculate what is the value of M1 and R1, and when the switch is closed, I'll calculate the value of M2 and R2. Right, this is for open condition and for closed condition. Now I'll be deriving these two values. I'll be deriving using the condition, that is switch open and switch close condition. Right, so let us move further. Now with switch open, I'll get, as we have previously seen, that is I have told L2 is equal to M R3 plus R4 plus R4 L1 divided by R3. So this was the expression that we have derived in a Heaviside's mutual inductance bridge. Now same expression, the circuit is similar, I'll be using the same expression I'll be using. Now here L2, it will be modified because switch is open. When switch is open, L2 and L both will be connected, so therefore I'll get L2 plus L, which is equal to M1 into R3 plus R4. Similarly R3 plus R4, this third and fourth branch, then R4 L1. So in this manner, the first expression I am getting. In the second expression I will be getting when the switch is closed. When the switch is closed, it means that this path will short, L2 and R2 will be removed from this circuit. So for that I am getting the expression L is equal to, similarly both the expressions I am getting. Now what I will do is I have to find out the value of L2. Now what I will do is I will subtract both this. Subtracting both this, I will get L2 is equal to M1 minus M2 1 plus R4 plus R3. So as I have earlier said, for open condition I will be calculating M1 and R1 I will be calculating. For closed condition I will be calculating M2 and R2 I will be calculating. So two different values of mutual inductance will be there. So on basis of that I can calculate what is the value of L2. Now let us calculate what is the value of R. The value of R, this is the unknown resistance that we have to adjust for the bridge balance condition. Right, now calculating the value of R, we have already seen that R2 was equal to R1 R4 by R3, that is in the Heaviside's bridge. When we were calculating, we had got the value of R2 in this manner. Now what I will do is, so when I am talking about switch open, when the switch is open, we can clearly make out that the resistance of the second arm will be R2 plus R. The first arm resistance will become R1 plus R1 because it's some value, the unknown resistance has to be adjusted to some value. R4 and R3's value will remain as it is. When the switch is closed, we can clearly make out this R2 is getting removed out. As R2 is getting removed out, I'll be writing it to be R2 is equal to R1 plus R2, that is small r2. R, because R2 is removed, capital R is equal to, in this manner I'll get the expression. Now what I'll do is I'll subtract both these expressions. Subtracting both the expressions, I'll get R2 is equal to R1 minus R2 into R4 by R3. So if I am making R3 is equal to R4, I can clearly get this expression. It will be cancelling out and this will become 1. So I'll get 2 L2 is equal to 2 into M1 minus M2 and R2 is equal to R1 minus R2. In this manner, I can clearly find out all the values of my inductance, self inductance, right? So self inductance value can also be calculated with the help of mutual inductance if the values of mutual inductance are known. This is why we will be using Campbell's modification of Heaviside bridge. Now moving further, let us discuss about what is a Wein's bridge. Now when we are talking about Wein's bridge is primarily used for frequency determination, right? So let us look into the circuit of a Wein's bridge. Now looking into the circuit of Wein's bridge, we can clearly make out in the first branch C1 and R1 are connected in parallel. In the second branch R2 and C2 are connected in series. Third branch and fourth branch both have resistors that are non-inductive in nature. And one more feature of this is we can clearly see here that R1 and R2 has a mechanical coupling. Mechanical coupling in such a manner that, for example, if there some order will be there, some arrangement will be there. For example, if value of this is 10, then for example I can set it to be equal, or I can set it to be in some ratio. In that manner, this mechanical coupling can be used. That is, adjusting one resistor, the second resistor's value will also get adjusted. This is for the reason why we are using mechanical coupling right? For in this similar manner, we'll go for the bridge balance equation. We know what is the bridge balance equation, as we have discussed in the previous lecture. Z1 Z4 is equal to Z2 into Z3. Now in the first arm I can see the capacitor and resistor are in series, in parallel. Therefore Z1 is equal to R1 divided by 1 plus j omega C1 R1. This is the value of impedance of the first arm. The impedance of the second arm I am getting it to be R2 minus j by omega C2. How I am getting? This is like R2 plus 1 by j omega C2. So when j is coming to the top, it is becoming minus j. Right, so in this manner I am getting the second impedance. I am getting the third impedance R3 and R4 as only R3 and R4. Now substituting all these values in the bridge balance equation. Now substituting this, what I have to do is I have to equate real part and imaginary part separately. So equating real part and imaginary part separately, this is the value of real part that I am getting. The imaginary part that I am getting, it is omega C1 R2 is equal to 1 by or minus 1 by omega C2 R1. This is equal to 0. Now when I am equating, I will get omega is equal to 1 by under root of R1 R2 C1 C2. Right. So this is, we know that omega is equal to 2 pi f, angular frequency, the relation between angular frequency and frequency. So in this manner I can calculate what is the value of frequency. The value of frequency is nothing but f is equal to 1 by 2 pi under root of R1 R2 C1 C2. Now if the values of R1 and R2 are known and the values of C1 and C2 are known, I can easily determine what is the frequency of the supply that I am connecting here. This is the AC supply that I am using. What is the frequency of AC supply that I have connected can easily be determined. Right. Now for example, let us take if the value of R1 and R2 is equal to R, or let the values be equal and the values of C1 and C2 be equal, because C1 and C2 are components that I am connecting. I will take the values of C1 and C2 to be same. R1 and R2, the mechanical coupling that is present. Now I will adjust the mechanical coupling in such a manner that both values will be same. Now when I am using that, I can clearly make out I will be getting the value of f is equal to 1 by 2 pi under root of r squared c squared, which is 1 by 2 pi rc. That is when the value of resistors that I have connected, R1 and R2 are equal, and the values of capacitors that I have selected, when both are equal, I can get the expression to be f is equal to 1 by 2 pi rc, a simplified expression for calculation of frequency. Right. Now here we can the Wein's bridge can be used for frequency determining device, or it can also be balanced using a single control, because only one mechanical coupling, I have to balance only one mechanical coupling. Right. Now the disadvantage of Wein's bridge is that it is difficult to balance unless the waveform is sinusoidal, and it cannot be balanced if harmonics are present in the applied voltage. So if harmonics are present, what I have to do is I have to combine a filter circuit in series with a Wein's bridge. Right. Now Wein's bridge can also be used for the measurement of capacitance, that is the unknown values of capacitance can also be measured using Wein's bridge.